from the pre-labs that I did look at, it's clear that there's kind of like a mix going on in the class. Some people were really kind of on track, kind of had a sense of what you're doing. Some people were really solid. Some people did not, even after me talking about it a bunch in, since the first day of class and having it in the book and showing examples, people still don't understand what an objective is, that it's a question, just like, how does the independent variable affect the dependent variable? So it's clear some people need to put a little more energy into like paying attention, be more detail oriented in the class, because this is not a class where you can kind of just like, I'll figure it out, or, it'll all make sense at some point, I guess. So you really need to be kind of detail oriented. And particularly the objective is the germ of the whole rest of the research project that you do, or any experiment. You have to have a really clear idea of, what is my question? What am I trying to figure out? What am I measuring? If you don't have that really clear in your head, you could spend hours doing stuff, but it's all going to be like a big confused mess. So you really need to be clear at the beginning of, this is my question. This is what I want to look at. And then everything kind of unfolds from there. And then again, the hypotheses always have to, one thing, hypotheses need to specifically address the variables you're looking at. Like if if it's the jumping lab and it's, how does someone's height, weight, or calf circumference affect their jump? Your hypothesis should not be talking about their age. That could be a source of variability or something, but hypothesis, which of these independent variables do you think is going to be important and why? Right? It has to be locked into the structure of the limited structure of what we're doing. So I set up one more just to kind of give you more experience. And also, I think having different people work together, because it's clear some people are getting this more easily than others. And I'm going to throw you into a bunch of random breakout rooms again. We have another one of these independent, dependent studies to analyze. Kind of like the same thing that we did last time with the, with the L-cysteine and the hangover symptoms. This one here is looking at cyber loafing. Cyber loafing just means using your technology for non-focused activities. Like if you're in classroom, so cyber loafing is like, kind of checking to see what did somebody wear on the red carpet or whatever. So cyber loafing is non-work related internet stuff on your phone or on your iPad or whatever. And this is a study, it just says, here's the abstract. You can just read it, investigates in-class and out-of-class cyber loafing activities of students in China, tests the relationship between those activities and academic performance. Again, so in class, out of class, and cyber loaf. Again, the definition of cyber loafing is just using your technology for something that is not appropriate for what you're, or is not work related. So what I'm going to want you all to do, I'm going to do the breakout rooms again. I'll give you like 15 minutes. I want you to come to a consensus in your group. Just again, what are the independent variables, dependent variables? State the objective. And I'll say it one more time. It should just be a question. If it doesn't have a question mark after it, you probably messed it up. It doesn't have to have anything about, in fact, it shouldn't have the methods in there. Some people have had methods in their objective. It's not the methods. People had, it should just be at the core. What is your question? With your very kind of specifically stated independent and dependent variables. And then what did they find? So are there any questions about what you are all about to embark on? All right, so this will give you guys a chance to not hear me yapping. And this says 4 to 5 participants per room, so this should work. So I will see you all in about 15 minutes or so. So have fun. All right, welcome back. So hopefully this is, if you do this, I mean, we'll be doing this again and again, but this is one of the things I really do want you to start getting a good feel for, is how to like really focus on what are we doing here? What's the question we're asking? What are the actual things we're measuring and observing? So for this one, what was the independent variable or variables for this study? Anybody?
In class and out of class cyberloafing?
Exactly. So there's like 2 independent variables on this one. They were measuring how much time people were messing around on their phones in class, that didn't have to do with the class, but then how much were they messing around on their phones outside of the class as well? And how about the dependent variable?
Academic performance.
Yeah, exactly. Academic performance. So it's just simple. And then what would be a nice, clear, concisely stated objective for this study?
What is the relationship between the in-class and out-of-class cyberloafing activities and the students' academic performances?
Exactly. So objective, it's always going to be something that simple and that straightforward. It's just what is the effect or correlation of the independent variables on the dependent variable. Done. So again, that's an important part of doing science this way, is having a very clear idea of what you're actually trying to figure out, because then you know what to measure. You know what relationships to look for to see what your answer is. And then how about what did they find? What was the result of this whole thing?
The in-class had a negative effect, and the out-of-class was actually beneficial in moderation in means of effort of recovery.
Yeah, so they found, it's not shocking, that there was a negative correlation with in-class cyberloafing and academic performance. People who keep checking their messages and trying to figure out, what's going on in their social life or whatever, while they're supposed to be like paying attention to the lecture, it's usually not a good thing. But outside, it talked about, so when we looked at in-class, or if we looked at academic, actually, right, the y-axis is always the dependent variable. So performance, and this is going to be cyberloafing down here. So when they looked at in-class cyberloafing, the more you cyberloafed, the worse you did. You got a kind of a negative correlation. They said for the out of class, it was a U-shaped. So, and like I mentioned, a lot of things actually aren't always linear. So U-shaped, meaning that people who had, a medium amount of cyberloafing. Actually, wait, did I do
the inverted U-shape?
Inverted, I did this backwards here. Let me, hold on one second. I spazzed on you all. Kind of like this. So it's not linear. It's saying the people who cyberloafed a whole lot didn't do as well, probably because they're just totally addicted to their phones or having trouble taking care of anything other than just checking out what's going on Instagram instead of trying to get their pre-labs done or whatever. But people who had no cyberloafing at all, these are probably people who actually aren't having any kind of relief or any. If you're too stressed about everything, you're also not going to do so well in your life. You got to find some kind of balance. This is kind of saying people who had some balance in their out of class loafing tended to actually do better in the class, which also you don't know. I mean, we wouldn't know this for sure unless we looked at it, though. That's one of the nice things about actually getting the data and checking it out. It makes sense, but we don't know for sure that would be true. But now we don't, true, I shouldn't say true, but this data supports that, having fun on your phone isn't necessarily a bad thing in moderation. You just probably shouldn't do it in your class, and you shouldn't do it to distraction all the time. So it was kind of a nice little study. And also hopefully for those of you who are still having trouble with independent, dependent variable objective, another round of trying to get comfortable and feeling like, oh, I know what he's talking about now.
Professor.
Uh-huh.
So I didn't end up adding this, but I was wondering if the fact that it was at the undergraduate level would have been something to include somewhere, maybe like in the description of the dependent variable, like academic performance at the undergraduate level. Or...
You could, yes, you could say, if you wanted to be more specific about the dependent variable, you could say academic performance of undergraduate students. So yeah, so that would be more specific.
Okay, thanks.
All right, so the reason why I'm kind of going over this again is because our lab today is going to be our first lab that is a hypothesis driven lab where there's a specific objective, and all of your analysis and discussion is going to rely on you having a well stated objective and a clearly stated hypothesis that then you can analyze your data and try to see if this is supported by your data. Unless these are solid, then the rest of your write-up is going to be kind of a mess. You need to have a kind of a focus on, what am I looking at here? What am I trying to figure out? So all, coming up with these parts, even though these are just a couple of sentences, if these sentences aren't kind of solid, then you could write 3 pages afterwards and it might all be for naught, because you're not actually addressing the core thing that you're supposed to be dealing with. So for today, the jumping lab. What, and I know some people, quite a few of you did this well. What was the objective for the jumping lab?
I said, is there a correlation between weight, height, BMI, and calf circumference on vertical jumping distance?
Yeah, so it's something as simple as that. Is there a correlation between these specific body measurements, their height, weight, and or their calf circumference? BMI is something we calculate from those, and their vertical jumping distance. That's all it is. But you need to be really clear that that is the question we're asking. Because that's also going to tell you which kind of variables we need to measure and which ones we're going to analyze. If you start adding in other things in there, or write other things in there, then you start just getting distracted from what is the core thing we're doing. So hypotheses. There's definitely, obviously, more than one hypothesis. What are some hypotheses? This is, hopefully we have a few people sharing different hypotheses here.
I said someone who has a larger calf circumference can jump higher because they may have more muscle to give them more power to jump.
All right, so she says someone who has, so notice that it's talking about about an actual variable we're measuring. It's saying, so she's saying there's going to be a positive correlation between calf circumference and jumping height. And then she's got a good, a compelling reason. A wider calf, may be due to, strong, larger calf muscles, which are going to generate force against gravity and let you jump. And that's something she can then check. Once we get the data, she can do some scatter plot and look at calf circumference versus jump height and see if the data actually supports her data, her hypothesis, right? So by having this clear hypothesis, she now knows exactly what she needs to do to analyze the data to see if the data supports her hypothesis. She's got to compare calf to jump. Another one.
The less that someone weighs, the higher they will be able to jump because there will be less gravity working against them.
All right, so here we have also, so this is, we're going to be a negative correlation between weight and jump height. And again, why? Because somebody weighs less, then they don't have to work as hard to push against gravity and get up off the ground. And again, it's going to be straightforward to see if the data supports that. Let's just do some scatter plot comparing weight to jump height and see if we see a negative correlation, right? So having a well-formulated hypothesis means you now know how to go into the data and see what the data has to say about your hypothesis. How about another one?
Height won't affect jumping height because there's no effect of gravity on the person's height.
So you could say that. I mean, no effective. I mean, there's other things we could, in fact, we'll talk about this more, but so you could have a negative hypothesis like that as well, and then look to make sure there's no correlation. What's another one?
For me, I said a taller individual would have advantage to jump higher because they have a large calf with more muscles, which allows them to fight gravity and jump higher.
So in this one, you'd have to be careful when you're doing the reasoning, like why, so taller person, larger calf, more muscles. So why not just stick with like the calf measurement there? Because I guess partly, I guess in general, people tend to be, you might want to say if the calf is proportional to their overall height, or something like that, you want to make some connection between their height and the size of their calf. When you're writing it, you want to be as kind of explicit as possible, like how the height is affecting the jump. So, but I mean, you could say something about like the height. If you're taller, then your limbs are going to be proportionally longer with larger muscles, and larger muscles could generate more force, something like that. More. I know I saw some other ones. I can also do this. Yeah, I can do this. I'm gonna. I landed on Leah.
Yes.
What is yours?
So mine, I put taller and lightweight individuals perform higher jumps because, so first of all, because lightweight people create more velocity and better force to leave the ground. Taller people have longer legs to help them lift the body higher.
Right. So this is kind of similar when I was talking to Amado, making sure that you have a kind of clear connection between like how is being lighter making you have more velocity. Right, the connection, you want to make sure that you are clear about the connection, like the reason, the why. You know, it could be you have less weight to, kind of accelerate against gravity or something. But you want to be a little more explicit when you say that. So if somebody is reading that, they say, yeah, oh, of course, I see what she's talking about, why that makes sense. Because sometimes people have steps in their head where I know what I'm talking about, but then when someone else looks at it, it's like they weren't in my head and they didn't see the extra little steps I was doing to connect these things. So when you write it out, you want to make sure you kind of connect all those steps, kind of explicitly longhand on the page. So we have Urs Tangalos.
Hello.
Hey, so what was your hypothesis?
For the jumping lab, I'm still working on it, but my hypothesis was that for the leaner, and I have it written down somewhere, it's not in my notebook yet since I'm working on it, but basically since the lighter weight have longer limbed and like just the better the BMI is, the higher the jump will be.
All right. So remember, you always any hypothesis needs to have a reason. You can't just and when you in BMI, nobody's mentioned BMI yet. When you use BMI, you have to make sure you're kind of clear about what aspect of BMI. Like BMI is different from these other ones where we can think more of like a linear relationship, because BMI has healthy versus unhealthy rather than, it's more categories rather than a continuous variable.
So you want specific to each perimeter tested. Okay, so that's why there's 4. Understood.
So Grace, you said something?
I was wondering if we could use BMI in our hypothesis.
Absolutely.
Okay.
Because BMI is just a calculation using the things we've already measured. So, and, particularly like with the calf, like, people who, I forget who was it Alexia? Did you have the calf versus the jump?
Yeah.
Yeah. So like for there, that is a reasonable hypothesis. But then there's always the problem, like, how do we know if the calf is large due to fat versus muscle? So we could use BMI there and say, a healthy BMI means you have a good proportion of lean tissue to fat. So let's look at calf versus jump, but just in the people with healthy BMI, because then we feel more sure that it's actually the calf has to do with muscle and it's not about being obese or something. So yeah, you can mix and match like that.
Thank you.
Sure. Any other ones?
I used BMI in my hypothesis, and I said if a person has a high BMI, then they'll have a lower jump height due to the extra weight or strain on the body that a high BMI implies. Is that too general?
Right. So there you'd have to, the problem is BMI is not a linear thing. What is a high BMI? I would say you want to use the specific numbers and also whether you're in the healthy or unhealthy range, because having a BMI of, actually a BMI of 17 is also unhealthy, and as a BMI of 30 is obese, but a BMI of 23, 24, or 20 are all considered just kind of healthy. So BMI,
So instead of using a term like high or low, say like use the categories you're saying, like overweight or obese.
Or I would say, healthy or unhealthy. Yeah, I'd say for BMI, and in fact, this is when we talk about this in a few moments after we look at the data. If you're analyzing BMI versus jump, you would probably do it more in categories with a bar chart, like healthy BMI versus unhealthy BMI versus a scatter plot that you would use for like calf circumference versus jump.
Because then unhealthy would also include the underweight category too, right?
Exactly.
Okay, yeah, that makes sense. Thank you.
Sure. All right, so then the last part, sources of variability. Most people did pretty well on this, although again, some people, again, you got to make sure you read. There were people who did not write sources of variability and instead like put in procedures or something, right? So what are sources of variability on this one?
I put past leg injuries or past back injuries.
Yeah, any kind of injury that's going to affect your ability to jump would be a huge source of variability. Right? If we were doing this in real life, then we would actually say that anybody who has injuries that affect their ability to jump are not going to take part in today's experiment. We talk about exclusionary criteria. If there's something about this person that makes them a bad fit for being a subject in a way that it's going to affect the data, then you can say, like, let's not have anybody in this thing, as a subject who has injuries that are going to affect their ability to jump. So we get rid of that source of variability. And more sources of variability.
Would whether or not they warmed up be a source of variability?
That could definitely be a source of variability too. Just, muscles get warmed up, even just, I would say mentally, even like you start kind of getting ready to go makes a difference. So yeah, and that's part of what we're going to do is what we would have done, part of practicing the jump is actually kind of getting moving, getting a feel for what it feels like, getting kind of stoked. We're not gonna. You're not required, but if you want, you're totally free to like just kind of go jump at home or whatever. It's fun. See how high you can go. So, what other sources of variability?
Body type, like if they're a weightlifter or if they don't work out, because if they lift weights, they're probably going to have a higher BMI.
Yeah, so I mean, definitely their conditioning and all of that, and even just how comfortable they are doing athletic things is probably going to make a difference. Again, we're not going to be able to control for that. We're going to just assume that enough people are a little above or below these true numbers. It's going to be part of the noise, but hopefully there's not some major bias where everybody is different from the normal population, so we're not going to see something that is typical. More.
The shoes that they're wearing.
Yeah, the shoes they're wearing. Again, that's why remember I talked about part of the reason you have to always think about sources of variability is, before you do the experiment, is so you can try to eliminate them if possible, so they're not going to contaminate your results, so you can trust what you find. So we think about, oh yeah, shoes. If they're wearing sandals or wearing like kind of basketball shoes, that's going to make a difference. So let's just have everybody take their shoes off. So then we know that that's not going to be a factor. What's another one?
I said how well fueled they are, like what they've eaten, as well as their level of alertness.
Yeah, that's gonna, I mean, actually, if someone's just eaten and they're about to jump and they feel like they're gonna barf if they push too hard, that's not gonna, that's gonna make a difference. And yeah, alertness, if you're super tired or you're super awake, or if you've just had 3 beers or you've just snorted a line of Coke or whatever, pharmaceutical alterations might make a difference. So those are all things, we are, we're not controlling. We're hoping like people are coming to school kind of basically at baseline. What other kinds of things?
The type of ground they're jumping off of?
Yeah, I mean, that could make a difference too. Again, when we do this in real life, we make sure that, because we have more than one jumping station, we try to make sure each of the jumping stations is identical, the same kind of floor, the same kind of wall, the same kind of, so it feels the same. And even like, attitude. We always tell, if you do sports psychology and visualization and all that kind of stuff, just kind of what you're thinking before you start makes a difference. And if someone's like, oh, this is stupid and I can't jump, I'm not athletic and I look stupid and it's like, there, I jumped, that's not going to be a good measure of what they can do. So kind of just trying to get everybody with an attitude of just like, do your best and jump and go for it. That's something we have to do in advance, is make sure we tell our subjects, kind of, we're all in this together, go. And even the style of it, the mechanics of the jump. It's part of the reason why we specifically mention exactly how the jump happens, is because there's all these different ways to jump. You could just jump with your legs. That's not going to be very good. You can use your arms, but then there's all sorts of lifts. There's like, you can go this way. There's Russian lifts. There's all sorts of lifts. It's like, how are you going to do the mechanics of the jump? It's going to affect how high you go. So, probably a lot more than your height, weight, or calf circumference. So we have to try to minimize the effect those have. So just kind of putting that out there, whenever you are designing things like this, you need to think about this ahead of time. It also means in your analysis later, when you're trying to figure out what happened or what the data says, sometimes you can say like, it looks like this source of variability actually was a problem, and it's affecting my ability to interpret the data. So, it comes in beforehand so you can design a good experiment, and then after so you can try to make sense of what you're seeing. All right, so blah, 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 blah. What we're gonna do now is just show you, 10 minutes of videos that would have been a lot of fun. I know it's not my fault. I didn't make the virus happen, but I still feel bad that you guys don't actually get to jump around in lab and stuff. So, but you get to watch me jump in lab. So yeah.
Are we collecting data during this?
No, you are not collecting data. So this is just showing you the process. And then as soon as I'm done with that, I will introduce a spreadsheet that has data on it. So you don't need to collect data right now. All you need to do is, we're going to spend 10 minutes so you can actually just, see in a physical realm what happened to actually collect the data. Okay, here we go. Share screen. All right, so we're in jumping lab. So now remember, so the jumping lab has 3 actual modules. There was the pre-lab for the jumping lab, which we've already been through. Right now we're in this jumping lab initial data gathering and analysis. This is just going to be data and initial analysis from our class. So we're gonna get some data just from a single class. You're gonna analyze it just looking at your hypothesis. But then next week, we're gonna be continuing the jumping lab. We're gonna bring in more data from other classes, and we're gonna do a more extensive analysis and look at hypotheses beyond just your hypothesis. Look at all of the independent variables and all that. So for today, we're going to keep a more limited view of what we're doing, a smaller data set just from a single class, a smaller amount of analysis just looking at your personal hypothesis. But we're not done with the jumping lab after today. So, but let's look at it, doing the jumping lab. And here we go. I hate that. It froze me with a stupid expression. It's not going away. Come on. Why isn't it working?
I don't know, but you have great socks in there.
Oh, I did that on purpose. I even mentioned it in the video. It's like when you know you're going to take your shoes off, you want to make sure you come into lab wearing good socks.
I like it.
Oh, thank you. All right, let me figure out what's going on here. Okay, almost there. This happened last time too. Okay, Firefox. Maybe Firefox is going to be my friend. Oh, Firefox. Here we go. Yep, this is it. So this is the jumping lab. In this lab, we're going to be taking a variety of measurements off of our subjects and then looking for correlations with their jumping height. So one of the measurements we're going to be taking is their height. Again, talking about sources of variability, your height is going to be really different depending if you're wearing platform shoes or you're barefoot. So before you take anybody's height, you got to make sure they don't got shoes on. No shoes. Another thing, some people, I don't have poofy hair, obviously. Some people have poofier hair. You want to make sure as you're measuring height that you compress down and you're actually getting their actual height and not the height that they're. So here we have meter sticks taped on the wall. I'm going to stand here straight and let's see.
Okay.
I'm going to show parallax.
What was that?
Show parallax. Like, you have to make sure it's parallel if you can over or underestimate it.
Oh, yeah. So it's important that it's parallel or perpendicular to the ruler in the wall, because you could measure too high by doing this or too low by doing this. So you want to have it completely perpendicular. And these meter sticks are marked with millimeter tick marks. So in this case, we want to measure to the nearest millimeter. And then you want to record that in your lab notebook. And also don't forget that there are 2 meter sticks taped here. So any person in this lab is definitely going to be over 1 meter tall. And then you reach to the nearest millimeter here. So in this case, it could be 1.665 8, and then you can convert that over to meters.
And in the actual lab, you would have more than one person take the same measurements, because even though it seems like a straightforward thing, there are so many slight variations, the exact angle of the meter stick, or just somebody's approximation of whether it's up or down 1 millimeter, that can actually lead to a different value. So to try to get at the true value, we take multiple measurements and we can then average them, and then assume that that average of those different measurements is approaching our true height. Oh, and I should mention here, this is a time when I usually bring up the idea of kind of the sanity check in the class. So you saw how there were 2 meter sticks taped on the wall. There's 1 meter stick here, and then there's another meter stick. And when she measured my height, it was, there's this 1 meter here, and then this one went up to, was it 65.8 centimeters here. I can't tell you how many times over the years where I look in people's data, or the data in their book, and there's like, oh, here's the height for Lily, and oh, we saw Lily is 65.8 centimeters tall. And actually they do 3. It's like, oh, there's 65.7 and 65. So it's average. So they do all these calculations and they're like, this is her height. And it's like, no, she's not a leprechaun. There's no way that could be her height. So we do what, we call like you can call it a sanity check. Or you can, in my world, sometimes we call it a dummy check or an idiot check even, although I usually don't say that because then people get all upset. It's like, it's like, so you can just call it a sanity check. But it's just like, did you make some like, whoa, I made some silly mistake here, that where my answer makes no sense at all. So you want to always do this. You're going to be measuring things or doing calculations. You always want to double check. Does your answer make any sense at all? And if it doesn't, you got to go back and figure out what happened. So this also means you have to have some intuition about metric units. I think most people growing up in the US here are all about feet and yards and stuff. And even though we use metric, people don't have a good intuition for it. And I know in Bio 110, they have this thing where they're trying to get you, like, your fingertip is like about a centimeter across, and your arms spread out are about a meter, right? So for this class, you should have as much of it, you try to get an intuition. A gram is about a jelly bean. A kilogram is about 2.2 pounds. So if you weigh something, you need to have some sense. Like a jelly bean can't weigh a kilogram, and a dog can't weigh 3 grams, right? You need to know kind of in general what these units are, so you can do a sanity check. You can't really do a sanity check and say, there's no way my lab mate is 65 centimeters tall if you don't really know what 65 centimeters means, right? In 6 centimeters, this is going to be 0.658 meters. So this is like only like 2/3 of a meter. It's about 2 feet. So think about, in the interest of kind of making sure we continue with the timing for today, I'm gonna probably push the calculations and stuff to next class, on Tuesday. But on Tuesday, we'll talk about sig figs and stuff you've seen in chemistry, but we need to revisit again, to make sure that you are using your numbers in a responsible way. So we're just, I'm doing this little tangent now because measuring the height, there's almost always one group, at least in the class, that will have their group members like 2 feet tall, and they'll type it into the spreadsheet and project it up on the screen and not really realizing like that makes no sense. So metric units are what we're going to use in this class, which means you need to make sure you've got kind of a good, good feel for them. Just like, if I said it's like, something weighs like, 10 pounds, you have a kind of sense I could carry it, but I'm going to feel it. But if somebody says, something is 65 centimeters, they don't know whether that's as tall as a person or as, tall as a dog. So it's, unless it's that dog that just died, that was as tall as a person. Did you see that? Like the world's tallest dog just died last week. He had a long, good life. He didn't die in an accident or something. All right, let's continue.
I just have a quick question. Sorry.
Sure.
So since we're not going to do the calculations today, I was just looking at the modules and it had like a place to submit your initial discussion.
Yeah,
Is that just going to be based on the video then?
I'm going to talk about that. We're going to finish these little videos and then we're going to talk about this initial analysis.
Okay, thank you.
Yeah, so that will all become clear in the next 15 minutes or so. So here we go, back to Jumping Labs, starring me and Tina. All right, so this next part is measuring the calf circumference. And again, here's another example where we need to bring in this idea of thinking about sources of variability before you actually do the experiment. Like, just like you have right-handed and left-handed people, there are people who are right-legged and left-legged, have a leg that they prefer. And they're going to probably have more muscles on their leg that they prefer. So the calves are probably not exactly the same. So it actually is going to be important to acknowledge that before we start and then come up with some way to deal with that. And the way we'll deal with it today is we'll measure the calf circumference of their dominant leg. That would be the leg, like if you were told, go hop on one foot from this side of the room to the other side of the room, which leg do you hop on? That is your dominant leg. So when your subject is getting ready for this, have them hop and see which leg they prefer, and then you want to measure that one. Also, I highly recommend, if you know you're taking your shoes off for this lab, wear fun socks.
All right, 37. And we're going to measure it 3 times with 3 different people measuring the subject's calf circumference, and then you're going to average that.
Okay. Oh, where to go? So that is showing in normal, again, the reason why you have 3 different people measure the calf, if you pull a little tighter and just squeeze a little more, it's going to be probably a difference of a millimeter or so Or if you go up or down a little bit, it's going to make a difference because the calf, keeps changing its shape. So, because there is this, kind of noise, this uncertainty, and even taking a straightforward measurement of somebody's height or their calf, we take the same measurement a few times and then we average them, and hopefully we're getting at the true value. The weight, we didn't put the weight in here because you all know what you do. You step on a scale and read the number on there. So that's how we did it. We just have these digital scales that you step on. So this is how we get the independent variables for this lab, is just take the measurements for all your subjects. And again, we have exclusionary criteria. We don't have someone can't be a subject if they're physically injured or something in a way that's going to make it impossible to do a good jump. And then after we get those measurements, in the calculate BMI, that's just a mathematical thing. That's easy. You just put it in the equation and grind and crank. So the next part here is going to show how we actually measure the jump itself. So this is how we're going to get the dependent variable. All right, so measure my height, my calf circumference multiple times, so we get hopefully as true a value as possible. We've also measured my weight standing on a scale. You all know how to do that. And now we're going to talk about our dependent variable in this whole experiment, the actual vertical jump height that I'm going to be able to do. A few things before we start that. Another source of variability is the actual mechanics of the jump itself. If you just kind of like go like that or whatever, it's going to make a big difference on how high you jump. And because we want to look across many subjects, we want to have a standard jump where everybody's doing the same mechanics, which I'll briefly show you. It's basically as described in your lab manual. You're standing vertically, your hands by your side, you bend your knees, and then you're going to extend your knees as you swing your arms upward. And you want to have your legs and your arms extending simultaneously so they both are at full extension at the same time. So there's this really nice kind of synergy that happens. And you also want to make sure you're using both arms. A lot of people have this tendency to like jump like that and just throw up one arm, and they have their half of their body is just kind of paralyzed. So you want to have your body straight, bending at your knees, and then in one smooth motion, explode up with your arms going up, your legs straightening, and to actually show how it's done, I'm going to have my pencil here where I'm actually going to be able to mark. Obviously, we want to see how high can I jump from my normal height. I don't care if a person is taller or shorter. They're going to be able to mark the paper higher or lower depending on their height. That has nothing to do with their jump. So what I care about is where do they mark it if they're just standing on the ground? And then I'm going to be able to jump and mark it at the peak of my jump. And then I'll see what's that relative distance. And so I'll do that. This is my baseline. I'm flat-footed. Now I'm going to go and do this jump. My legs. Ready? And I want to, again, every time you jump, you're obviously not going to jump exactly the same height. So another thing we're going to do, just like we did multiple measurements for the height and all that, we do multiple measurements for the jump. Go like that. Again, holding the pencil the exact same angle that I'm going to mark at the top of my jump. I'm going to get ready. Straight body, bent legs. Go up. There's the second jump. And I'll get ready. And one last time. And my lab partner, if I go in like this, my lab partner's got to say like, whoa, that wasn't a, it's nice to watch you jump, but that wasn't a jump we can count because you didn't have the proper form. So as a person, making sure the experiment is done correctly, you need to, you don't want to throw away data just because it isn't what you thought it should be, but you don't want to take data if they actually didn't do the procedure properly. That's a good thing. So I'll do my third jump, bend my knees, stand up. And now I have 3 little marks up there. And now it's time to measure how high my vertical jump is so we can see how it correlates with my height, my weight, my calf circumference, and some other things that will.
All right, so next it's time to measure David's jumps here. So carefully, without falling off, you want to get up here. We use the metric system of any ruler that you have. And then, of course, it's not very handy for me to record this. I'm going to have to yell out the numbers for my lab partner to write down in the lab notebook. So I'm going to go from the baseline to the first mark here at the highest point. And it's going to be 47 centimeters and a half a centimeter. So 47.5 centimeters. 47.5. All right, second jump. It's going to be 46.2 centimeters. 46.2. And the third is 47.0 centimeters. So those are the 3 jumps that they can do. All right?
Okie dokie. So that gives you a sense of how we actually get the data. Obviously you are not doing it. Instead, what I have here this is a file that you are going to use for your initial analysis that has, we did actually include sex in here because it turns out sex is actually a very interesting variable to look at in this experiment. So you could consider it as like kind of another independent variable. We have the weight, the height, calf, BMI, and the jump. So here is the data. And so basically now we'll come back here. I'm gonna stop sharing here. What's the next step? So we had, we started with our objective, hypothesis, source of variability, the procedure, that's got to be in your lab book. And now we just got the data, which normally you would have recorded, but you're going to just have as the spreadsheet. So what's next? What's the next step in your lab write-up now?
The discussion.
Yeah, so the discussion, and how are we going to approach this? We're going to have to figure out, we're going to have to kind of look at the data. What are we going to look at? How are we going to approach this? What's the first thing we're going to look at?
You compare your data to your hypothesis.
Exactly. Right? Did everybody hear Leah? Right. The first thing, now that you have your data, now you're going to be able to look, does it support your hypothesis or not? So what you're going to have to do is analyze your data to see whether or not your hypothesis is supported. So we are gonna, the first step here is we're gonna like analyze to see if it supports your hypothesis or not.
Is that in the discussion portion or in the data portion?
You know, sometimes people talk about the data as kind of just generating the graphs and things like that. So it's kind of, it doesn't matter so much. Yeah, data usually is just kind of recording the stuff that you're observing. And then as you start actually playing with it, it's becoming more discussion. But, you know, often taking the data and creating your initial graphs and things that you can then use in your discussion to support your points, you know, I'd say it doesn't matter. It's irrelevant. So what this means is for this first part, so what I do want for Tuesday, I do want, at this point, everybody, not everybody, but most of you have done this and this and this. And this you just paste in. And this you also are just gonna basically paste in because I'm giving it to you as a Excel. So at this point, everybody, not everybody, most of you have got this all pretty much done. So what I want you to do for Tuesday is do this initial analysis. You know, in reality, whenever you do an experiment, you check to see if the data supports your hypothesis, but then you also look deeper, right? Because why stop? You got all the data. Why not see if there's something interesting that it's saying, even if it's not exactly what you're looking for? So next week, we'll talk more about kind of this more extended analysis, but for Tuesday, I want you to basically analyze the data and see if it supports your hypothesis or not, you know? And that's going to look different for different people. Different people have different hypotheses. What you write here is not going to be the same as somebody else writes because they'll have a different thing they're looking at. Eventually, we are going to learn how to do all the graphing in Excel and all that. But for this, I would like you to do it longhand just to kind of prove to yourself that you know how to do graphing. And it's important that you know graphing and don't just let a computer do it. So initial analysis, you know, check your hypothesis. You know, hand-drawn graphs. And so for instance, oh, now I'm forgetting who had the calf.
I did.
So Alexia, so for Alexia, so how is Alexia going to use this data that we've got and analyze it to see if it supports her hypothesis that calf circumference is positively correlated with jump height?
Can she make a graph like a scatter plot?
Yeah, exactly. Right. Did everyone hear Raina? It's like if you're gonna look for a correlation between two continuous variables like calf circumference and jump height, you use a scatter plot. You know, you put the dependent variable here, you put the independent variable here, and then you put all your data here and see, is it a positive correlation, a negative correlation, not correlated? I'll do it. You know, I'm going to just do it. I'm going to do my best.
So just double check. You want us to paste in the spreadsheet data, but then make our own graphs for it?
Exactly.
Okay.
Right. The nice thing, your lab book is made out of graph paper. So you've got graph paper in it. I am using a ruler here to make this as pretty as possible. This graph is going to be quantitative. You care about, the spacing and everything. It means when you're doing your axes, this is going to be my jump height in centimeters. I want to make sure however many centimeters it is from one to the next is the same as to the next, is the same to the next, to the next, to the next. People start getting sloppy and start making these graphs that look like a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's like, what? It's like, you can't, don't get sloppy. Make sure, if this is 1 and 2, this is 3, and that, you need to make sure that your graph is very regular. Let me get rid of all that crap there. This is going to be my calf circumference, also centimeters. Always label axes. Always use units. So that's always important. And then for this calf circumference, I am actually looking at the data. I don't want to bring it on right now. If I look at the jumps, the smallest jump is 14. The biggest jump is 61. So before you do the graph, you kind of need to think about the overall range so you know how to label your axes. The calves, again, I'm just looking at the spreadsheet off screen right now. The calves go anywhere from, let's see, 30 to 45. So that gives me the range so it means for my calf circumference, if this is 30, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, it's actually perfect. This is going to be 31, 32, 33, 34, 35, 36, 37, 38, 9, 40, 41, 42, 43, 44, 45. Calf in centimeters. You want your graph to be kind of spread out. You don't want all of the data to be stuck in one corner of it or something. So that's why you think about what is the range ahead of time so you can make your axes make sense. For the jump height, 14 to 16, if I say like this is 10, maybe this will be 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. Notice, in this case, I have each tick mark is 5 centimeters, but I just make sure for that axis that I am consistent. So now I'm set. I've got my range of jumps is going to fit here nicely. My range of calves is going to fit on the x-axis. And then each subject, it just becomes a dot. Right? So if I if I look at this thing, it says calf 35, jump 61. So 35 goes right about there. The next subject, calf is 44, jump is 27. So now I'm at 44. I'm there. And now next, I have the next subject is the calf is 37, the jump is 40. And the dot goes there. Right, so these, right, this is how I make a scatter plot. Each one of these is a subject. The next subject is calf is 45 and 41 and a half, jump is 54. You know, etc. So each subject becomes a dot on this graph. Right? Eventually, I'll just have a whole bunch of dots. And then I have to decide, does it look like there is a correlation? Right? If my dots, does everybody understand how I'm constructing this graph? You know, so
Yes.
if it ended up looking like this, I would probably say like, it doesn't look like there's much of a correlation. But if it looked something more like this, it's always going to be messy. But if I looked at something like this, then it looks, oh, again, and you were pretty good at eyeballing the best fit line. Next week, we'll have Excel actually calculate the linear regression, the best fit line, and it'll all be easier. But, you know, a rule of thumb, I think one of the ones they tell you in Bio 110 even is if you find a line where like half the dots are above and half the dots are below, that's a good fit. So you'll find a best fit line and then, you know, you'll say like, oh, it looks like the data seems to support my hypothesis. If it looks like this, the calf circumference seems to be positively correlated, or maybe you're going to say like, unfortunately, the data does not seem correlated. So it's likely that, you know, calf circumference is not a good measure of jumping, and probably because there's so much variation on how much the circumference is due to fat versus muscle or something. But so that's all I want you to do for this first part, is do some initial analysis just for your, not for everything, just for your thing, and an initial conclusion. Does the data seem to support your hypothesis or not? That's all I want. We're going to do a lot more involved analysis for this later, but for Tuesday, it's just this. What about BMI? What if I wanted to know whether or not, I forget who it was. What if I said healthy BMI people are going to jump higher than unhealthy BMI? How am I going to do that? How am I going to analyze that?
You calculate the weights and the height.
Bar graph.
I'm going to use bar graphs. You know, if I'm going to do this, what I would do is, if I could just share screen again. You know, here are the BMIs, right? So I'm going to say any BMI that is between 18 and 25 is healthy. So I'm just going to highlight those. So let's say that one, 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 that one. So all the ones I just highlighted, those are the healthy BMI people. So I can just take their jumps and get the average jump for the healthy BMI people, right? It's just add them up and divide by the number of jumps. I can then also get the average jump for the unhealthy BMI people, add those up and divide by the number of unhealthy jumps, right? And then I just make a bar graph. You know, average jump height in centimeters. And then I'm going to have categories, you know, healthy BMI, unhealthy BMI. You know, and there'll be like 2 bars. Right. So if you're trying to analyze categories like BMI, you do it more like that. And then you could answer your question again. Does the healthy BMI people seem to jump higher in general than unhealthy BMI?
Could you also do a scatter plot with 2 different like color dots or shape dots and then compare those 2 relationships?
Or
would that,
for what?
I guess that wouldn't make sense. I don't know. I was thinking for doing the healthy versus unhealthy BMI and then versus the jump height, but do a scatter plot with different colors for healthy versus unhealthy, but I guess they wouldn't really like overlap on that graph then.
And it wouldn't really give you the averages of the jumps.
Yeah. No, that makes sense. Kind of answered my own question.
Right. I mean, the other thing that, like we talked about, like calf, you know, but just for the people with healthy BMI, it could be interesting, like with the people who are highlighted here, do a scatter plot of calf versus jump, but only for the highlighted people. Just throw out all the other data because those are the unhealthy. So then I could see what does calf circumference versus jump look like, but just for the healthy BMI, right? So that's another thing you could do, where we're just selecting a subset of the data, like the healthy BMI subset, and then doing a scatter plot just of them to see how calf versus jump looks like. So, right, I'm going to stop sharing then. So are there any questions about this?
I just have a few. For the graphs, are we doing 2 then? One for just the original class data you're giving us, and then one for the overall class data?
Wait,
just one graph?
It's just one graph using the data that we got. The data in that spreadsheet that is available to you, and then look at that using the lens of your specific hypothesis and see if this data seems to support your hypothesis or not.
Okay, and then we'll find that data under the lab portion on the modules?
It's like, yeah, doing the lab. It's the same module that has, or the same page that has the videos in it.
So we're only doing graphs for like the independent variables that are in our hypothesis, not all independent variables?
Correct. Next week, we will be extending the analysis and we will do all of them. And then it'll be easier because we're going to have Excel churning through lots of data and spitting out graphs for us. But for today, I just want you to look at this kind of more your specific hypothesis. And I do want you to do it manually just to kind of flex your kind of graphing muscles so you feel comfortable that, you know, how this is going. Because I know some people are like graphs, but some people get all flustered with graphs. So it's good to kind of get comfortable with them again.
So since you want this discussion turned in before Tuesday, do you want us to leave a page for the second half that we're doing on Tuesdays to write the discussion that you want?
No, I would say just it's going to take way more than a page to do the next part. So wherever you leave off with your initial analysis, you're just going to be continuing on from there. So yeah, so you're going to turn in, the objective, it's going to be a redo of your objective hypothesis, not a repicture, but then it makes sure you have the methods in there as well, and you have the data, and then this initial analysis with your initial kind of conclusion on what it says about your hypothesis, and then just leave it there. Take a picture, turn it in, and then next week we'll go much more into detail about how to kind of milk this for a lot more. If you have questions, you can email me or whatever as you get into this. And yeah, next week again, we'll talk a little more about sig figs and things like that, and precision versus accuracy. But I wanted to make sure that we are kind of ending at 12:30, and it's 12:28.